Jai Hind, dear children. Welcome to physics class. Today we are going to start the new chapter, moving charges and magnetism. First, introduction of the chapter. Hans Christian Ørsted observed that a compass needle suffers a deflection when placed near a current carrying conductor. This is the experimental arrangement to show that there is a magnetic field around current carrying conductor. Consider a conductor AB which is connected to a battery and a key through a rheostat. A compass needle is placed parallel and below to the current carrying conductor. When current passes through the conductor, we can see the compass needle shows a slight deflection towards one direction. This shows there is a magnetic field around current carrying conductor. This discovery gave the first evidence of connection between electric and magnetic phenomenon. The direction of magnetic field around current carrying conductor is given by right hand thumb rule. Right hand thumb rule states that hold the current carrying conductor with your right hand so that thumb points in the direction of current, then the four fingers will wrap in the direction of magnetic field. Now we are going to discuss about Lorentz force. We know if a charge is placed in an external electric field E, what happens to the charge? It experiences a force. That force is given by F equals QE. This force is called electric force, isn't it? Fe. So force experienced by a charge in a uniform electric field E is Fe equal to QE, and this force is called Lorentz electric force. This is called Lorentz electric force. Similarly, when a charge Q is moving with a velocity v in a uniform magnetic field B, there is a force experienced by the charge, and that force is given by F equal to Q into V cross B, where V represents the velocity, B represents the external magnetic field applied, and Q is the charge. So that force is called Lorentz magnetic force. So that force can be represented by Fb, and that force is called Lorentz magnetic force. Lorentz magnetic force. Okay, so two forces are there. When a charge is placed in an electric field, Lorentz electric force F equal to QE. In magnetic field, the charge is moving with a velocity v. It experiences a force Fb equals Q into V cross B, and that force is Lorentz magnetic force. Similarly, if a charge is moving with a velocity in an external magnetic field and electric field, if both electric field and magnetic field are applied, and if the charge is moving in the electric field and magnetic field, we have the total force experienced is equal to total electric force plus total magnetic force. And the total electric force is QE, and the total magnetic force is Q into V cross B. And the total force is called Lorentz force. So if both electric field and magnetic field are applied, then Lorentz force is given by Lorentz force is F equal to QE plus Q into V cross B. If you want to take Q outside, that force can be written as F equal to Q into E plus V cross B. Vectors we can take. Okay, so if both electric field and magnetic field are applied, then the charge experience the Lorentz force F equal to QE plus Q into V cross B, or F equal to QE into E plus V cross B. This is called Lorentz force. If the charge is at rest in external electric field and magnetic field, in that case V will be 0, then it experiences only Lorentz electric force. Okay, so that is the importance of Lorentz force. So Lorentz force means if a charge is moving with a velocity in an external electric field and magnetic field, the total force experienced by the charge is Lorentz force, which is given by Lorentz electric force plus Lorentz magnetic force. The direction of Lorentz electric force is always in the direction of electric field, because F equal to QE, no? So direction of force is in the direction of electric field, and the direction of magnetic force is always perpendicular to the plane containing velocity and magnetic field, vector V and vector B, because it is V cross B. So the direction of magnetic force is always perpendicular to the plane containing vector V and vector B. Now the expression of magnetic force help us to define the unit of magnetic field. So we have magnetic force is given by Fb equals Q into V cross B, isn't it? Or we can write Fb equal to QVB sin theta, where theta is the angle between V and B. Or from this formula, magnetic field can be written as B equals magnetic force divided by QV sin theta. Using this formula you can write. Then substituting the unit of force Newton, then charge coulomb, velocity meter per second. Second comes to the numerator. So the unit of magnetic field becomes Newton second per coulomb meter, and it is called a Tesla. So Tesla is the SI unit of magnetic field. Tesla is represented by capital T. And usually Tesla is a rather large unit, and hence a smaller unit called Gauss. One Gauss is 10 raised to minus 4 Tesla is also often used. And we know Earth has a magnetic field, and the magnetic field of Earth is about 3.6 into 10 raised to minus 5 Tesla. Okay children, magnetic force on a current carrying conductor. For this, consider a conductor of length L, area of cross section A, carrying current I is placed in an external magnetic field B. Here the electrons inside the conductor drift with velocity Vd, which is opposite to the direction of current. Here each electron experiences a magnetic force. We know Lorentz magnetic force is given by F equals Q into V cross B, isn't it? So each electron experiences a magnetic force Fb, magnetic force Fb equals Q into V cross B. Here we can write Fb can be written as, since there are electrons E into, and the electrons are moving with the drift velocity Vd. Therefore we can write Vd cross B. Okay. Capital N be the total number of electrons inside the conductor, and small n be the number of electrons per unit volume. Okay. Now we can write small n equal to number of electrons per unit volume is total number of electrons divided by volume, isn't it? Is equal to capital N divided by, here the volume is area of cross section is A, and the conductor of length L. So N divided by AL. Hence total force on the conductor is, we know force on one electron inside the conductor, each electron inside the conductor is Fb equal to Q into V cross B. So force on the total number of electrons is N into E into Vd cross B. Total number of electrons inside the conductor is N, therefore total force F equal to N E into Vd cross B. But what is N? Capital N can be written as number of electrons per unit volume into area of cross section into length into E into Vd cross B. Okay. But what is this NAE into Vd? NAE Vd, we know NAE Vd, that is equal to current I. Already we have studied I equal to NAE Vd in current electricity chapter. So this can be written as NAE Vd can be written as I into L cross B. So force experienced by all the electrons inside the conductor, or force on a current carrying conductor which is placed in external magnetic field, is given by F equal to I into L cross B. If a current carrying conductor of length L carrying current I, if it is placed in an external magnetic field B, then the force experienced is given by F equals I into L cross B. Or it can be written as F equal to ILB sin theta, where theta is the angle between length and the magnetic field. What is the direction of length? The direction of length is in the direction of current. Okay, so F equal to I into L cross B, or F equal to ILB sin theta. Theta is the angle between current or length in the direction of current and magnetic field. And the direction of this force is given by Fleming's left hand rule. So Fleming's left hand rule, using Fleming's left hand rule, we can find out the direction of force on the current carrying conductor placed in an external magnetic field. Fleming's left hand rule, using this Fleming's left hand rule, we can find out the direction. So Fleming's left hand rule is stretch the thumb, forefinger and middle finger of your left hand mutually perpendicular to each other. Then the forefinger represents the direction of magnetic field, middle finger represents the direction of current, then thumb gives the direction of force on the conductor. Okay, so this is Fleming's left hand rule. If you stretch the forefinger, middle finger and thumb of your left hand mutually perpendicular to each other, so that forefinger represents the direction of magnetic field, middle finger represents the direction of current, then thumb points in the direction of force. So using Fleming's left hand rule, we can find out the direction of force on the current carrying conductor. So we have studied two formula for force. Force acting on a charge moving with velocity v in an external magnetic field is F equals Q into V cross B. Another one, magnetic force on a current carrying conductor placed in an external magnetic field is F equals I into L cross B. Thus we have studied magnetic force on charge Q moving with velocity v in magnetic field B is F equal to Q into V cross B, and magnetic force on conductor of length L carrying current I placed in magnetic field is I into L cross B.